Overview 2.04, Composite Figures, where we will be solving mathematical problems involving the area of two-dimensional figures composed of triangles, quadrilaterals, and polygons. We will also determine the area of a composite figure using coordinates. A composite figure is made up of several simple geometric shapes, such as triangles, rectangles, squares, circles, and even semicircles. Overlapping a square and a circle forms a composite figure. We're going to drag the square to overlap the circle as its diameter, connecting points A to point F and point B to point G. How is the radius of the circle related to the side of the square? To find the total area, how will you need to modify the formula for the area of a circle? So to solve problems involving composite figures, you will be required to detach the figure by drawing dashed lines to identify the specific geometric shape. Check out these other examples of composite figures. Think about individual shapes that are combined to produce the whole edge. Notice here, where would be the best location for a dashed line segment to be drawn to decompose? That kind of means to just cut it. A dashed line segment can be drawn from point A to point B. Notice that we now have a rectangle and a semicircle. The unique area formula can be applied to each shape that has been identified. In other words, the area of a rectangle is length times width, and the area of a semicircle is half pi times radius squared. Therefore, the equation for finding the area of this composite figure, meaning that we put them together, would be length times width plus, which is our rectangle, plus half times pi times radius squared. The diameter of this semicircle is AB. AB is equal to CD because the opposite sides of a rectangle are congruent. Therefore, dividing its length of 8 by 2 will result in the radius. Think about the fact that this is the diameter of this circle right here. So if I divide that by 2, I get the radius. Okay. So I'm going to say radius squared, which is 4. Let's look at another one. Find the area of this composite figure. All units are in centimeters, but remember, for all of our assignments, we assume the unit is there. We do not put it into the exit ticket or into our answers. So we're going to use this figure right here, and we're going to decompose it by drawing 2 horizontal dashed line segments to form 3 rectangles. Notice the missing length of the middle rectangle can be determined by using the horizontal length. So this length right here can be determined by saying x plus 4 equals 20. So this plus this equals all of this. Now we can subtract 4 from both sides, and we see that this line is equal to 16. We can substitute 16, and now we can say 4 plus x plus 2 equals 10 in order to find this part of the line right here. Now we know that the top of the rectangle length is 8 centimeters and the width is 4 centimeters. The middle rectangle is 16, and the width is 4. The bottom rectangle is 20, and the width is 2. I'm going to go ahead and substitute length times width for all 3 of my rectangles. Length times width for the top, length times width for the middle, length times width for the bottom. I would get 32 plus 64 plus 40. Now I can add all of those together to find the full area of my composite figure. 136 centimeters squared is the area of the composite figure. Composite figures can be graphed in coordinate planes as well. We're going to determine the area of the figure involved when it involves identifying the dimensions of each shape using the coordinates of endpoints. If the endpoints of any horizontal or vertical line segment, radius, or diameter lie on the intersection of the grid lines, you can simply count the blocks. Otherwise, you can calculate any dimensions by utilizing that wonderful distance formula. So here we have this figure. We want to go ahead and find the area of this composite figure. We're going to decompose the figure by drawing a horizontal dashed line segment from -6,3 to point D to form this rectangle and this trapezoid. You could also draw a vertical dashed line from D to 1, 1 to form a rectangle and a triangle if you wanted to. So we know that the rectangle's length is 7 and its width is 2. We know that the trapezoid's top base is 7 because it matches the length of the rectangle, and its height is 2. We also know that the bottom base is 10. So we're going to create an equation for the area of both composite figures. Notice the area of a rectangle is length times width, and area of a trapezoid is height divided by 2 times base 1 plus base 2. Now let's plug in the information that we know or substitute our values. So 7 times 2 plus 2 divided by 2, top base, and 7 plus 10. I don't know why my slides are empty. Times 2 is 14 plus 2 divided by 2 is 1. I can go ahead and do what's in the parentheses first, which is 17. Therefore, 1 times 17 is 17. So my total area is 14 plus 17, which equals 31. Oh, there's my slide. I have no idea what happened there. Let's go ahead and look at finding the area of this decomposite figure. We're going to decompose the figure into simple geometric shapes. So we're going to draw the dashed line right here from -2, -5 to point D. This is going to form 2 rectangles. Now, because these lines are not vertical or horizontal, they are diagonal, I'm going to need to use the distance formula. Remember that the distance formula is x1 minus x2 squared plus y1 minus y2 squared. So I'm going to use each of my coordinates, -4, -2 for my x's, -3, -3 for my y's, or I should say negative 4, 2 for my x's, negative 3, 3 for my y's. I'm going to subtract those values. I get negative 6. Negative 6 squared is 36. 36 plus 36 is 72. The square root of 72 exact is 6 to the square root of 2. Now, I'm going to take just a minute to explain this because I feel that it's very important. Anytime that you're asked to simplify a radical, you're going to look for the perfect square and its factors. So you're going to think, what can I do to multiply? What two numbers can I multiply to get 72? So 1 times 72, 2 times 36, and you're going to keep going. 3 times blah, blah, blah. Now notice that 6 times 6 is 36. So I can stop there if I want to because I found the perfect square. So finding the perfect square would be like saying 36 times 2. Okay. So that is equal, the square root of 72 is equal to the square root of 36 times 72. Notice that it's also equal to the square root of 36 times the square root of 2. Well, notice that this is my perfect square. This is why we call it simplifying a radical, because the square root of 36 is 6. Now, I can't simplify the square root of 2, so I leave it just as it is. Now, that's just a side note there, so hopefully that made sense. If it didn't, go back, rewind, watch it again. This is important when you're using the distance formula, the Pythagorean theorem. Anytime that you're using squares, area, anything like that, you're going to need this information because this is what we call the exact answer. All right, so on the next triangle, I go through the distance formula, or rectangle, I go through the distance formula and I use my coordinates. For x, it was 2, 4, and for y, it was 3 and 1. I subtract both of those to find the difference. Notice that I get negative 2 times negative 2, which gives me a positive, and 2 times 2, which gives me a positive. So I get the square root of 8. Again, simplified is the square root of 2, or is 2 times the square root of 2. My next calculation, applying the distance formula to DE and EF of the smaller rectangle, I find that it's 3 times the square root of 2 and 2 times the square root of 2. Now I'm going to plug each of those answers in. So I'm going to say 6 times the square root of 2 times 2 times the square root of 2. Notice that I'm going to get 6 times 2, which is 12, and the square root of 2 times the square root of 2, which is the square root of 4. Then I'm going to add all of this together to see that my total is 36. If you have any questions about this lesson, please feel free to text me or email me.